In algebra, a polynomial's zero is the specific value of x that causes the entire function to evaluate to exactly zero. This algebraic property has a direct geometric counterpart. When mapped onto a coordinate plane, these zeros appear as the physical x-intercepts where the curve crosses the horizontal axis. For quadratics, we have reliable, universal tools like the quadratic formula to pinpoint these locations. Often, we can find these points even faster by recognizing the arithmetic factors that multiply together to form the equation. At this level, predicting where a curve will cross the axis is a straightforward process with a guaranteed solution. But as functions scale into third, fourth, and sixth degrees, the geometry becomes more complex. The universal formulas we rely on simply do not exist for these higher dimensions. Take a sixth-degree polynomial like this one. We cannot rely on plotting random points or guessing inputs to find the zeros. The high powers make the manual calculation of coordinates too inefficient for precise graphing. Instead, we find the exact intercepts by working through a systematic hierarchy of factoring techniques. This approach breaks down high-degree expressions into a series of smaller, manageable equations that we already know how to solve. To find the intercepts, we set the function equal to 0. The first step in our hierarchy is to identify the greatest common factor, the largest monomial present in every term. By pulling x squared out, we leave a simpler fourth-degree trinomial inside the brackets. This initial step provides our first intercept immediately. If we set that isolated x squared to 0, we find our first crossing point at the origin. Extracting the global common factor is an essential first pass that reduces the degree of the remaining equation. Now we can isolate the remaining fourth-degree trinomial. This expression is unique because it contains no odd-powered terms, no x cubed and no x to the first power. This allows for quadratic reduction. Because the powers are even, we can temporarily treat x squared as a single variable, transforming the expression. In this form, the equation factors easily into t minus 4 squared. When we replace our temporary variable with the original x squared, the complex fourth-degree structure is gone. We can then use the difference of squares to break the remaining binomial into its simplest linear factors. This gives us the full set of algebraic zeros for the function, 0, 2, and -2. By recognizing these structural patterns, we can use basic quadratic tools to solve a sixth-degree equation. Now, consider a different case, a cubic polynomial with 4 distinct terms. Here, our first step fails. Because the final term is a constant 12, there is no shared x variable to extract from the entire function. Instead, we use step 3, factoring by grouping. We split the 4 terms into 2 separate pairs and look for factors within those smaller groups. We extract x squared from the first pair and -3 from the second. This reveals a shared binomial factor, x minus 4, present in both sections. We can then factor out that shared binomial, rewriting the cubic as the product of 2 simpler parts. Setting each part to 0 gives us our intercepts, 4, along with the positive and negative square root of 3. This technique works because the ratio between the coefficients in the first pair of terms matches the ratio in the second pair. We can now verify these algebraic results by looking at the actual curves. Graphing software verifies if our calculated zeros match the physical intercepts. The plotted sixth-degree curve crosses the x-axis exactly at -2, 0, and 2. The cubic function follows suit, its intercepts mapping precisely to 4 and the 2 square roots of 3. While a graph shows us where the intercepts are located, the factoring hierarchy explains the numerical relationship that creates those points. To complete our understanding of the function's position, we also need to find the y-intercept. This is straightforward when an equation is already in factored form. Unlike x-intercepts, which require solving an equation, the y-intercept is found by simply evaluating the function at x equals 0. By substituting 0 into the expression, the calculation shows the curve crosses the vertical axis at +3. These combined methods allow us to reliably identify all the major crossing points on the entire coordinate plane. While not every high-degree polynomial can be solved with basic radicals, identifying these tiered patterns allows us to decompose many complex expressions into their linear and quadratic components.